In this video, we're going to go through several examples when we will learn how to integrate using only properties in a definition of the definite integral. So we don't know yet the main theorem you're going to learn right after this video, how to make your life easier. For now, we're going to teach you how to use geometry. Don't be afraid of this word geometry. It's actually not that bad. You will see that basically we're using a bunch of triangles and circles. So reviewing some definitions and properties of the integrals, and we're going to be using these to work with several examples. Example number 1. Evaluate the integral by interpreting it in terms of areas to 2 decimal places. And the integral is from 0 to 10, absolute value of 6x minus 1 dx. Okay, first, if you don't know how to start, sketch a graph, right? And in this case, it actually should be a good sketch. It should not be just some pretending picture, because we will need the exact numbers in this case. Do you guys know how to plot absolute values functions? Some of you probably are freaking out about this and grabbing your calculators right away to use graphing calculators. But actually, you just need to plot the function without absolute value, which is not too bad, and then use x-axis as a mirror, because y should be positive or 0 only. So, how to plot 6x minus 1? I'm just plugging 2 convenient points, because 2 points define the line. So when x is 0, y is negative 1. And then when y is 0, x is over here, 1, 6, right? Y is 0, x equals 1, 6. That's the root. Then this line I'm talking about looks like this. This is a line 6x minus 1. However, absolute value makes x-axis to be magical. It has a magical property, means that x now is a mirror. So it's going to be mirroring everything that's below x-axis and taking it up. So this part below actually should be cross away and put up like this. That's the graph of the absolute value of 6x minus 1. This is how it looks like. And I have it ready for you over here, looking nicely. And we're asked to look not for the whole minus infinity to infinity domain. We're working actually only from 0 to 10. And these restrictions create triangles. I'll put one line over here, and there's a line over here already. So I need to find the area of this tiny triangle over here, A1, from 0 to this point, which we actually already found, that's 1, 6, and this huge triangle A2. Pay attention that both of them are above x-axis, so they both will be positive. Then it means the total area will be A1 plus A2. And that will be my integral from 0 to 10. So if one of the areas are below x-axis, we subtract that area, if you remember. Now, to find those areas, we're going to just use geometry. A1, the area of the triangle is 1/2. So just to remind you, area of the triangle, I will put little triangle over here, is 1/2 height and times base. Height times base, right? So we just need to find the points of intersections for this small triangle to know the height and the base. For A1, I have a small triangle like this. It's over here. And a point over here is 1, 6. So everything is 1, 6. Did you guys get how I got 1, 6? What this point is, this is my x-intercept, right? So, this is where my x-intercept. X-intercept means y equals to 0. So when y is 0, I need to solve 6x minus 1 equals to 0. X is 1, 6. This is how I found that point. Then from 0 to 1, 6, the base is 1, 6. What is the height? Well, the height is actually y-intercept, so x is 0. When x is 0, this point is -1 or 1. Well, we're working with y equals absolute value 6x minus 1. So when x is 0, y is absolute value of -1. That's 1. So the height over here is 1. The height over here is 1. Then I can write down that area 1 is 1/2. I usually put it first, not to forget. And then height is 1 and base is 1/6. So the total is 1/12. That's a very small area, which makes sense from the graph. Look at how tiny the triangle is. The big triangle has base 10 or not? What this base is. This is not 10. It's actually 10 minus this little piece 1/6, right? 10 minus 1/6 is 60 over 6 minus 1/6, which is 59 over 6. That's my base. To find the height, I need to plug my 10 into the function. F of 10, that's going to be over here. F of 10 is, so it's going to be absolute value, 6 times 10, that's 60 minus 1. So that's actually 59. Then the height is 59. Area 2 is 1/2. Then width or base is 59 over 6 times 59. Grab your calculator and you will have something like 290.08. That's a huge area. Makes sense because that triangle is really big. Total area or integral, I would say integral from 0 to 10 of absolute value of 6x minus 1 dx will be exactly area 1 plus area 2 because both are above x-axis, and that's going to be 1 over 12 plus 290.08, which is approximately 290.17, and that's the final answer. So we used properties of integrals and the properties where we can add pieces, right? We can integrate first. You know what we did? We integrate first from 0 to 1/6, the same function 6x minus 1 dx. And then we would keep integrating from 1/6 to 10, 6x minus 1 dx. And that's the property which allows us to break the big interval into smaller intervals using these points I circled right now as a connector. From 0 to connector, then plus to connector to 10. That gives me integral from 0 to 10 of 6x minus 1 dx. That's the property from the list over here. Integral from a to b will be integral from a to the connector p plus integral from connector p to b. And this connector can be anything you want, and you can have many of them. You can have hundreds and hundreds of pieces. In this case, we just wanted a small triangle plus a big triangle. One more example is hiding over here. One more example with absolute value to make sure that you are comfortable with that. In this case, evaluate the integral by interpreting it in terms of the areas. The integral is from -4 to 4, 3 minus absolute value of x. Well, the graph of absolute value of x looks like this. Negative absolute value of x will look like this. And then there is a vertical shift up by 3 units because we're adding 3. That's why it jumped to here. Make sense? This is how the graph looks like. It's in front of you. Since we're working from -4 to 4, it becomes from -4 to 4. It means we need to find areas of how many triangles? 1, 2, both are below x-axis, so those will be negative. And in pink, I will do this big one. 3. 3 triangles if you want to see it this way. Then you can break the integral into how many pieces? And I'll show you not a legal notation, but everyone using it, and they always punish students when students using it in class or on the exam. but actually many professors using it. The integral from -4 to 4 will be integral from -4 to this point, which I can see from the graph is -3. We're going to check it later. Plus integral from -3 to this one is 3, plus integral from 3 to 4. And you see I don't put any function there and don't put any dx, which is completely wrong. Don't tell anyone I did that, but honestly everyone doing it this way because it's just a fast notation. That represents how we're breaking it. From -4 to 4 will be a breaking point -3 and 3, then a breaking point 3 and 3, and finally endpoints -4 and 4, which match with the original integral. Then you need to find three triangles. And I don't like this idea. Because, do you guys notice anything? I'll make a copy. Do you remember what it means to be an even function? An even function is like a parabola. If you use y-axis to fold the function like a butterfly, left-hand side will match with the right-hand side. So actually, it means everything on the left is the same as everything on the right from the y-axis, because y-axis here is axis of symmetry. So even functions are symmetric with respect to y-axis. Then I just need to find two triangles. This one, which is positive area because it's above x-axis. This one will be negative. I'll find total everything on the right and then just double the result. This way, the integral from -4 to 4 will be double the result of the integral from 0 to 3 plus 3 to 4 due to symmetry. And that's legal to do, and we'll be doing that quite a lot. Okay, let's do that. I will call the first area A1 and the second area A2. So what was the function? Y equals 3 minus absolute value of x. Let's find the first integral. Well, what is my y-intercept? When x is 0, y is 3. That's why this one is 3. You should not just trust the graph. I always would prefer to check. So this one is 0 and 3, which means the height is 3. What is this point? I claimed it is 3 because it looks like on a graph, but that's not right to do. I never trust the graphs. I always check myself. And I recommend you to do the same because calculators do lie when they graph functions. To find x-intercept, y should be 0. When y is 0, absolute value of x is 3. So x is plus or minus 3. Makes sense. This one is -3 and this one is 3. So the whole base over here is 3. A1 will be 1/2. I always put it first not to forget. Times height is 3. Base is 3. That's 9/2. And this one is positive. A2 will be negative because it's below x-axis. I will find the positive value of it and then I will subtract it. So I know that this number is 3 and this number over here is 4. So this length or the base, it will be 4 minus 3, which is 1. Now I need to find how far below x-axis this function goes. To do that, I will plug the endpoint into my function. What is f at 4 if f is 3 minus absolute value of x? 3 minus absolute value of 4. That's -1. So for both cases, it goes down to -1 on the left and on the right. Then these depths, right? Imagine it's a pit. So this is like we were digging the pit and now it's empty over there. So how deep the pit is? It's not -1 deep for you to know. It's 1 unit deep. Make sense? But since it's below x-axis, that's why it's negative. But we just need to calculate the depths. That's 1. Then the second area will be 1/2. The base was 1 because 4 minus 3. And the depth was 1 as well. So the total is 1/2. Now, since the first area was above x-axis, but the second one was below x-axis, the total area, A, and that area is, I would say, right, area on the right from y-axis, will be A1 minus A2, which is 9/2 minus 1/2, which is 8/2, which is 4. Then final area, which is integral from -4 to 4, 3 minus absolute value of x dx, will be the total area, which is doubled area on the right. So that's 8. And that's the final answer. Due to symmetry. Look at the graph again. Basically, I found everything on the right and multiplied by 2 because the graph is symmetric with respect to y-axis. Since everything on the right ended up to 4, when I multiplied by 2, I got 8. One more example. 3. Evaluate the integral below, and the integral is integral from -15 to 15, a square root of 225 minus x squared dx. Looks complicated. I would see it this way, and you guys should definitely get used to see its square roots. Write down the integrand. The integrand is the function we are integrating. That is square root 225 minus x squared. For now, let's remember that y should be positive or 0 because the square root is positive or 0. But I will recommend you to square both sides. That's going to be y squared equals 225 minus x squared, and move variables to the left. X squared becomes positive plus y squared equals 225. Does this remind you anything? Maybe something from geometry? Well, that's a circle. A circle centered at 0, and the radius is 15. Because the formula for circles centered at the center is x squared plus y squared. X squared plus y squared equals radius squared. Since we've got 225 on the right hand side, radius is 15. The graph of the circle looks like this. For this concrete circle, it's centered at 0 because x squared plus y squared, and the radius is 15. 15 minus 15 minus 15. Now we're going back to the remember part I mentioned to you. I said remember the fact that originally we were not given with x squared y squared piece. We were given with the y equals square root piece. That means y should be always non-negative. So actually we're talking only about upper half of the circle. Here it is. Since we're talking about only upper half of the circle, we can find the area of the total circle and then just divide by 2. Now it requires you to remember the area of the circle. Area of the circle. While I'm writing it, who knows the area of the circle? We definitely have something 2 pi r squared, and so on. Since we're talking about area, remember that it is r squared piece. So area of this circle is pi r squared. Then in our case, area will be 1/2 of pi r squared because we're talking about hemicircle. Hemicircle means half of the circle. Hemicircle. So we're dividing by 2 pi r squared. That's going to be 1/2 pi. R is 15, so r squared is 225. Or the nice way to answer the question is area or the integral. Remember, we're talking about integral here. And the integral is integral from -15 to 15, a square root 225 minus x squared dx is area, which is pi 225 over 2. Actually, that's not very nice to write it down. It should be 225 over 2 pi. That's the most standard way. Found it. Finally, the last example, example 4. This is the example that students get confused about pretty often. Find a and b if something is given, and we're given several integrals and some kind of connection between them. So we have integral from 0 to 10 of the function f of x minus integral from 0 to 7 of the function f of x. And that gives me the integral from a to b of the same function. Okay, the good thing that the functions are all the same, that allows us to glue these things together. And this is what I'm going to show you. Let's just move this guy over here with a negative sign to the right and see what's going to happen. Maybe it will help you. Then I will have integral from 0 to 7 f of x dx plus integral from a to b f of x dx equals whatever was on the left hand side, integral from 0 to 10 f of x dx. Then we need to check that property we already used before, the gluing property. The gluing property tells me that if I'm working on the integral from 0 and the biggest number is 10 and the intermediate number is 7, I have right to integrate only from 0 to 7, right? From 0 to 7. Then I will be adding the integral from 7 to 10. That will be different color. And that will give me integral from, what do you think? 0 to 10. 0 to 10. That's like the gluing property. So 7 here is intermediate breaking point. Well, this is what exactly happening. I'm having integral from 0 to 7, then from a to b, and it gives me the integral from 0 to 10. So we started from 0 and ended at 0. That's a good part. Then the gluing point is 7. Then this a should be the same in order to glue those two integrals. From 0 to 7, from 7 to b, just like I did here, right? From 0 to 7 plus 7 to b. So now I know that a should be 7. And then, since the ending point is 10, and we started from 0, b should be 10. b should be 10. And this is how we found both. So again, we're doing it from 0 to 7 plus from 7 to 10. That gives me integral from 0 to 10. So basically they asked us to match the gluing point and what the end point is going to be. And here's the simulation from 0 to 7, from 0 to 7, plus from 7 to 10, gives me in green from 0 to 10. That's all. Basically, in this example, you just need to have good imagination and remember the gluing property. The gluing property makes sense because if we're just adding tons of areas, or maybe looking like a triangle, maybe the other one will be, I don't know, a piece of the sign, stuff like that. And then the third one will be exponential function, flying up. And of course, since all of these are after all just areas, we can glue the way we want, from 0 to a, from a to b, from b to c, and so on, as much as we want to break it down. That's all. A very nice list of examples. Hopefully it was helpful for you. Keep working on more examples to feel more comfortable with this, and see you next time.